Hey Stars, welcome back.
Thank you. Hello.
The data satanist.
Yep. There were some comments in LinkedIn.
Yeah, interesting one. The first comment was is a typo, so no, not this is the right one.
Yeah.
What I wanted, what I'm interested in is the company. So what you said is that you make the scientist. So you are providing services to scientists to make their work easier. My
Well,
question is,
mhm.
what is it? So, I mean, if someone buys a scientist buys your software,
Mhm.
what is it? So, is it like how to compare it with whatever we know?
So yeah, scientific software is similar to any other software. It's just the
Hmm.
actual domain is different. Maybe some problems are a little different than in other fields. So I'll give you an example of our flagship software. So let's say you're a
And you
chemist.
have multiple products.
Yeah. Yeah.
Oh, okay, interesting. Okay, there go with the flagship. What's the name of the flagship?
It's called Pixel. Um,
Hmm.
so you're a chemist and you
Hmm.
synthesize something in the lab. Actually, you don't really know how much of the right stuff you produced. Maybe it broke down. Maybe the reaction didn't actually succeed. There are many reasons why you actually won't receive the molecule that you wanted to synthesize. So, in order to check what's there, you take a small drop from the vial and you inject into some instruments that measure physical properties. Some measure the wavelength at which it absorbs light. Others measure the masses of molecules.
Hmm.
And from these physical properties, you're trying to deduce what's there, whether it's the expected stuff or not, and how much is there.
Hmm.
And for instance, my software, it takes the files from those instruments and visualizes, does the calculations and predicts and detects the peaks on there. Like you get the signal, you get the peaks on this signal, and yeah, you need to figure out if it's the actual substance.
So it means that the first added value is you understand the format of the instruments. So you have
Yeah,
a parser.
yeah. Unfortunately, all these vendors they produce their own formats, which are not very they are binary, so it's very hard to work with them without the specification, etc.
So how many formats are you supporting?
Maybe like 10.
Hmm. And
Yeah.
what instruments are there? Is like scales or what? How to imagine such an instrument or how it looks like?
So, for instance, a popular one is mass spectrometer. Basically, you inject a mixture of whatever,
Hmm.
and those molecules have to be ionized, so they have a charge, and then you apply electric field, and then they start flying. And the
Hmm.
smaller molecules they fly faster, and the bigger one, of course,
Hmm.
they fly slower because they receive the same amount of energy. And then by
Hmm.
measuring how fast it reaches the detector, you can
Yeah,
predict the
cool.
mass. So
It's
this
a
is a mass
cool hack.
spectrometer.
What's the name of the system?
Mass spectrometer, a
Uh
type
huh.
of detector.
Okay.
Yeah.
And what comes out? What you can do with it? You can evaluate what's inside
So
or.
so let's say you have this mixture of stuff that you hope this is what you're looking for.
Hmm.
Um, and of course, a molecule it consists of different atoms, and different atoms have different isotopes, different
Hmm.
elements. This is actually the same element, but it weighs differently.
Hmm.
So a molecule reaches the detector, and you receive that its mass is 100, for instance.
Hmm.
There can be, if you know there is only one molecule that can weigh 100,
Hmm.
the units are called daltons, 100 daltons, then you know this is the molecule that you're looking for. But sometimes it's possible that two different molecules, they actually weigh the same.
Hmm.
So by knowing the proportions of, let's say, chlorine has
Hmm.
two primary isotopes, and you know the proportions of them in the atmosphere,
Hmm.
in the air, or whatever. So it means that for if you receive 100 molecules on the detector, some of them, the percentage will have different mass.
Mhm.
right? So knowing the proportions, which elements your molecule consists of, you can predict the proportions of the signal, of how much of which weight you receive, and from this pattern, you then try to figure out if this is actually your molecule, if it's consistent with your mathematical expectations or not.
Oh, and your system is helping automating the entire procedure because it will
Yeah,
receive all the data and will try to visualize the data, right? So
yeah,
does the instrument visualize something, anything, or
yeah,
just?
yeah. You have the signal.
Mhm.
You know, you have the peaks. You have these mass spectra. You enter which molecules you expect in general to be maybe in this vial, and then it looks at it calculates which masses. There's like quite
Mhm.
comprehensive combinatorial thing
And
calculation.
this happens in your software.
Yeah, yeah. They
This is
upload
not
the
what the instrument just produces the raw data, right?
yeah. The instrument produces measurements, which masses and how much the intensity, how high the intensity, and then from that data you need to figure out what that actually means.
But what the scientists would do without your software then? I mean, this is mission impossible to do it on paper, right?
There's of course software that comes from with the vendors. There are
Mm-hmm.
different software packages that
Mm-hmm.
do the same. They can also analyze it themselves, writing some scripts if they have a library to read that format. So there are other
So, but you
ways.
will
Yeah,
have to create some scripts and do some. So there's no integrated solution.
there are some solutions. Yeah, this is not the first solution ever
Yeah.
created. We're just trying to make this process as easy as possible because most scientific software is you open a page and you have like 100 buttons and all of them look the same and you're lost.
Mm-hmm.
We're trying to bring some proper user experience to scientists
So your
and
software
speed.
supports the usual process. So the idea is that the scientists already know, okay, they don't have the 500 buttons, but you will show the right button at the right time, right?
Yeah, yeah, yeah. And
Okay.
instead of buttons and entering in the forms, you can drag and drop, etc., etc. So
Okay. And how? Okay. So there's a measurement. It is parsed. Is it demanding at this point, or is it just a typical CRUD software? So is it like heavy stuff happening in inside Java or?
yeah, it can be quite heavy. Like most of the functionality, of course, is a regular software. But in
Mhm.
order to parse and in order to do those calculations, it can be quite demanding. So, and it's very different. Like some measurements are low resolution, and it may be a couple of megabytes per
Mhm.
one such injection. Others could be a gigabyte of data. And you have to crunch all this data to find find the right stuff there. So it can take some time, yeah. And this is one of the problems with this kind of software because most of them are very slow. We're trying to optimize these things.
So you spend lots of time optimization. So parse 1 gig of binary data as fast as possible, right?
Yeah, yeah. Parse and then store, of course. So
We are
yeah.
storing this in a relational database, or?
The simplest setup is yes,
Mhm.
just push it everything to Postgres, but Postgres has
Mhm.
limitations in how much the data you can store.
So you
And
have big
so
data problem as well.
yeah, yeah. Unfortunately, right now there's not that many users, so we don't yet run into these problems. But at some point, we'll have to think more about performance and scalability. Like if you store it in S3, S3 already solves a lot of these problems. But
Mhm.
then, of course, the network part, because if many people upload at the same time,
Mhm.
that is still a problem that you need to solve.
Yeah, it's interesting challenge. So basically what this system does is they do some experiments to find or change a molecule, a new molecule, or change existing one, or something like this, right?
So yeah, if you are working in pharma environment, you can
Mm-hmm.
be trying to synthesize some molecule that can be like eventually a drug.
Mm-hmm.
But of course, there are many stages to this. So first, you synthesize a simpler thing. You measure, you do some toxicology or other assays whether it satisfies your needs. If not, you may want to do a different modification. So there could be like a lot of modifications. And at very beginning, you don't even know where to start. So you may
Mm-hmm.
actually run like synthesize a million molecules and try, well, maybe this one works or that one works. So the ones that worked, they call them hits because they actually hit the target, the protein. And then you try to modify those hits to make it better and better eventually.
So they know what they want to have, and the question is whether the experiments are resulting in the expectation, right? So this is what your software had to do. So they know the target.
So they know what they want to synthesize. Once they synthesize it, they want to know whether the synthesis actually succeeded.
How synthesis looks like. So what's behind synthesis? So how to imagine that?
So as a chemist, you know what, at least in the early drug discovery, this is mainly where I work. This is where people are trying to find those hits that actually attach to a protein or to some other target molecule. They found these original hits and they do the modifications. So this hit, they call it a core, and then they do the modifications. So the amount of modifications can be very large. You can put all sorts of stuff on that molecule.
How they do it is like
they have so-called libraries. A library is a set of molecules that are similar to each other and that can participate in the same type of reaction. So frequently these days, on the early drug discovery stages, they don't just run one synthesis at a time. They take like hundreds of similar looking molecules that have the same reactive conditions, and they run, let's say, 1,000 of synthetic reactions. So after
pardon, because if you what interests me, how it looks like. So they have like drag and drop on the machine. This is the molecules, and then then is a machine which maps the drag and drop actions to some, I don't know how to call it. So that there should be a relation to a real stuff, or is it pure simulation? What we are talking about? No.
First, they do this simulation thing in the computer. They call it enumeration. At least this is one of the ways of doing this. So basically, you draw a molecule and you draw another piece of molecule, and you say, well, this piece connects to this piece on the first molecule, and this piece is similar. It's the same in every molecule in the library. So if you run through this enumeration process, you end up with many molecules that connects in the same piece, but the rest is different.
Yeah. The same interface, different implementation.
You can say that, yeah.
Okay.
So this happens in the computer, and we don't know at this point whether it actually will succeed. This is one of the reasons why you need this analysis part.
Okay. The first was enumeration. The second part is an analysis, is called, right?
So the first part enumeration. The second part, you go do actual synthesis. You order stuff from
what
some
is
provider.
the synthesis? Is the machine because you said there's a molecule. So I'm in a computer and I drag and drop my library or molecule, but something has to happen in real world. So there should be a machine which does something with the input, right?
Yeah. So you figure out what you want to combine, like the reactants and reagents. You send this to some store. Either it's an inside the pharma company or it's in some vendor. You order the right amounts and you receive, let's say, powder of that molecule. Now,
so you have to order. You have to order actually what you did. You have to order somewhere, and you get back the substance.
Yeah, some of it is going to be in-house. Some of it is going to be outside. The thing the hit that you generated originally, like the one that actually is the biggest part of the molecule, oftentimes you synthesize it within the company, but the rest is more or less generic molecules. That's why they're called libraries, probably. I don't know. Well, library is a big set of similar looking things. So these are commercially available. You order them. You have a powder. And depending on the experiment, so the ones that I used to work with more when I was doing synthetic software is you put it into some solvent, you dissolve
Mm-hmm.
both participants of the reaction, both reactants, and then you use either manually or use robotics that will mix these mixtures together.
Ah. Uh-huh.
You probably will leave it for some hours, maybe a day. You may be mixing it, you may be heating it, sonicating, putting some light on it. Those are different reaction conditions. Once the reaction has passed, you want to quench it to shut it down. So you put a lot of solvent so that it's very dissolved. And from there, you go to that analysis part where
Uh-huh.
you take the piece and inject it into instrument and see whether those reactions succeeded and which actually succeeded.
And this is where your software kicks in. So this is
Yeah.
where, and the process was called synthesis. This was the part of mixing and doing, right?
Yeah, that part was reaction synthesis. Yeah.
Which is a little bit
makes sense.
unbelievable for me that the process is not automated, because I would imagine there is a machine which does this automatically, under specific conditions, because you can introduce a lot of errors. You can mixing longer or shorter, or the temperature may vary.
So part of my previous project, it was a very big project, was automating these things, but not everything. So we were automating a lot of mixing, because if you have 1,000 reactions, doing
Yeah.
manual pipetting and mixing them
Yeah.
is very tedious, and you can actually make mistakes, especially
Yeah, exactly.
if you're doing thousands of them. It's not like milliliters. It's not like a spoon of stuff. It's a stuff that you put on put a simple, very small drop. If you look at it on a drop on the table, like, it's gonna evaporate very quickly. Like, it's a very tiny drop. So you do want to automate this with robotics. These are called liquid handlers because, well, they handle liquids. And basically it's like a syringe that aspirates stuff and then dispenses it into a different vial. But still, you usually take that container manually and put it into a mixer, shaker, whatever.
And why manually?
Sometimes
why? Because it is too hard, or why? What's the problem? Because for me, it doesn't sound that hard to make it work. Because what it reminds me is a paint job of cars. There's also I thought it was easy, but it's not that easy, because if the cars are painted, there's mixtures. You can have only specific sequence of paints in the specific, because you cannot have black color and immediately afterwards white color, because it will you have to some cleaning and stuff. So it is actually quite complicated procedure, and it's fully automated actually. And of course, it's a little bit harder. What is, but I think it should be doable, right?
So, depending on where you are in the drug discovery or manufacturing, when you're in research, you try to experiment in different stuff, different processes. If you are in production, then you're repeating the same stuff over and over again.
Yeah.
So if you're in production, then yes, you want to automate everything as much as possible. If you're in research and you're trying, shuffling, it doesn't pay off most of the time to automate.
Yeah, but let's imagine I had such a machine, and I said to the machine, mix slowly, to the other, mix fast, and mix fast with the temperature, and it does it for me. It's almost like an agent. I just say what I would like to do, and that will this should work, right? Why not? Because if you are mixing, I mean, this is really hard to capture how long I mixed, what I did. This is like you need almost a camera to film you and to record you what you actually did, right?
First of all, it's not just mixture. There can be many different steps. Second, robotics has to be calibrated all the time. It breaks all the time. It's not like you set it up. Like if it's simple, if it does the same thing over and over again, then probably, yeah. If it's very different things, it takes time to program those robots. They have to be recalibrated once in a while. They break. So they're not as convenient as it may sound.
There's a case for LC, This is LC20.
EDC?
LC, your company, This
LC. Yeah. There's a lot of hardware stuff too. Like, it's not just software part that
Mhm.
But software part two, yeah, it's a lot of
But
work. A lot of
I
work.
think it has to come. If you think about this, in one point of time, it should be that way, right?
It's a
Right?
very hot topic. Yeah, if you go to
It
conference, like
is okay.
there are
I thought
very
it. Mhm.
there are very like called lab of the future. It's a common
Ah,
umbrella term of automation, robotics plus software plus plus etc. So it's a very hot topic, and many people are trying to do. It's just oftentimes the return on investment is very
oh,
low
this
if
could
you are
be
in the early drug discovery stage. If you're
okay.
later,
This could be.
sure.
Mhm. Okay. So was a legit question, not like it was completely stupid. So it's actually someone looks at that and it could
Yeah,
add value if it works out. And of course, as always, if you start with automation early, it introduces errors, but in one point of time should be better than humans, right?
if it repeats the same thing, yeah.
No, but you also saying this, but if I think about this, there's only limited things you can do, right? You can mix stuff, so we had it, but then there is the duration with the solvent, the amounts, duration, light, temperature, pressure. If you think about this, what you could apply to such things, right?
And then you need to physically transfer it to a refrigerator or to a heater or
Yeah.
to a shaker. So
But
there's
this
a
is even
physical.
some, the cooking machines do this. They can, they can cook, they can bake, and they can mix. I would say if you I mean, I know this is not comparable, but just from the idea, it should be doable. It's not like technology is not there. It
Yeah,
is
but
just.
then you change the layout of the lab just a
Mhm.
little,
Mhm.
and it screws everything over, right? So it happens. People do this. It's just the return on investment is not as good as you might think.
Yeah, because the people are really good, maybe in the
Yeah,
research.
yeah.
Yeah.
It's actually from the human perspective, like transferring stuff from one place to another place is not that hard. It's just if it's happening at night, that's where you benefit robots more.
Okay. So this was your flagship software. So it understands instruments binary formats, which can be huge, and then it reads, tries to find the right things, and then it stores everything and in Postgres, and I think it makes searchable over long term, so you can
Yep.
find your experiments earlier. So there's maybe a standard format, which stores the experiments, right?
Yeah. Yeah. Yeah.
And you can export them maybe to the next machine, to the next instrument, or not? Is there like the next step where you can say, okay, I can pick this and do something with it now?
There can be next steps,
Mhm.
but they're very different from team to team,
Okay.
company to company. So they would usually do this more script on their own, but
Mhm.
the data is there. Yeah.
Okay. And how many forms or how complex is your UI user interface?
So the biggest complication is not the forms; it's the charts, and
Hmm.
those charts are like you can modify things, you can drag and
Oh.
drop, you can
Hmm.
click there here with one button held, and yeah.
Oh, okay.
So that's the biggest part, like charts, different
Hmm.
statistics, visualizing statistics. We have we're using some expression languages to do mathematics, custom mathematics that person may want to do. So this is more complicated than forms.
Okay, so you need almost like a DSL to get better quality data filtering and grouping and stuff like that.
Yeah, we use there's a library called Jexel
Uh-huh.
on the UI. So we took it, added some new features using that expression language.
Hmm. And cool. And what you as a flagship? You have also other products, right?
Yeah. Another other products are much smaller. One of them is a nice one. So we took Excalidraw,
What? What?
Excalidraw,
No.
the drawing tool, the diagrams. It's a very popular tool these days.
Okay.
We used to use Miro, but
Amido. Okay. Uh-huh.
used to, but
Uh-huh.
now we use Excalidraw. It's a very nice tool, and they have an open source version, which is of course just UI, no backend. So we took that and we added some capabilities to draw chemical structures. So basically, it's like a generic diagramming tool, plus you can embed actual structures there. So yeah, very
Yeah,
very
that's
pretty.
cool.
Yeah, most of the
Sca-
job, of course, is not ours. It's the Excalidraw who did the tooling, but yeah. We just
How is
combined it with
X scally draw?
Excalidraw.
Mhm,
EXCAL.
mhm, mhm. Excalibur whiteboard.
Yeah,
Mhm. Looks nice.
very nice, very nice.
Mhm. And what you can do, what you can load in your Excalibur version?
So chemical structures. Basically, there are some editors where you can draw chemical structures, and they're stored in. There are just several formats to store the molecules, and you can generate a picture, an SVG, and insert it into whiteboards. So that we automate that part.
This Excalibur draw I'm drawing right now reminds me on Draw.io. This is what I use a lot. You know Draw.io? This is
Yeah, I
what
heard
is.
about it. I've never used it, but people reference it.
Draw.io is very similar to this one. It is less polished, maybe, but I think maybe they are based on the same engine because it looks similar. And Draw.io is very popular in architecture diagrams, cloud diagrams, on the AWS documentation. So it's usually everything is Draw.io. So I use it, for all UML-like stuff.
Yeah, recently I started to use this Excalibur, and it solves all my problems. So yeah, like it very much.
Yeah,
our version, you will like it. It's called Malbrett. So it's like German Malbrett, where you draw the pictures, but it's Malbrett, like molecules.
Like mal bread. Bread is like desk, right?
Yeah.
Yeah, cool. And so it's also a product, and which molecule format? So how to load the stuff? So what is a molecule format?
Yeah, so a molecule is a graph. You connect one atom to another atom. So usually what we learned in school in chemistry, it's a chemical formula, like H2O. But H2O, it just says how many atoms are there, but it doesn't say how they're connected. A proper chemical format, it stores the connection between atoms, and now you can draw a picture from that.
What is the proper chemical format? How to call it, or how it looks like, or what is it?
So the simple one is called smiles because it resembles an emoji, because it's like there's like in organic chemistry you have a lot of carbon, so you have a lot of C, and it looks like smileys. So this is a simple one. It's basically just a string, and you figure out, well, this atom goes after another atom, then they're connected, for instance. There are more comprehensive formats that store the actual graph. And a graph is just, you have an element and you say to which element it's connected. Then the next row says this element is connected also to another element. And another part of the information is what type of a bond. You can have singular bonds, covalent bonds, double bonds, etc. And there are some very weird complications that I guess only chemists will understand. But basically, it's a connection.
But if you have this smile or the other format and you parse it, you can draw 3D structure out of that.
Yeah, and once you draw it, you can also store, that editor will also store the connection between atoms, and there are usually the 3D locations.
So is it like 3D? Can you rotate it as well? No.
Depending on the editor. Yeah. Usually chemists don't.
Bread, no. Your bread cannot do that, right?
No, we use the other editor. Most of the time, 3D will be more complicated than you prefer. Like a typical chemist would prefer to look with a 2D structure rather than 3D. There are different. When the bond is different, like it goes on you from the screen or it goes into the screen, we just put a different symbol, different line type, and they understand that it goes into the screen.
Okay. And is it popular under the scientists, or is like well received? They really use it, or is it more like a gag what you created?
So we're a small company. No one knows about us yet. So
but now after
have that many users after the podcast, of course. But those who do, they like it. And I really like it.
But if you show this to a scientist, so you had some users, so they say, okay, it's useful.
Yeah, it's useful. Mostly people currently use it for their own notes to make presentations. Yeah, this is the primary use case at the moment.
Yeah, because for me it's a complete new area, but there are some parallels to software, right?
Yep.
So we use Draw.io exactly for that. So I also experimented recently with various formats, how to capture some ideas, and this is not a different, except this is in 3D.
Mm-hmm.
And we could actually also do 3D with layers, but it also never took off, right?
Yeah, 3D looks. It's
What I
hard.
wanted to do actually, it was in the early application server days. I think it was maybe 2005, and there was a 3D was there was it's OpenGL. There was a Java Joggle. There was a Java 3D library,
Mm-hmm.
and the application server, the JBoss, they you could actually ask the JBoss to know what's deployed, what's the relation between the applications. So what I
Mm-hmm.
wanted to do is like 3D visualization, So you can be in the server and see the application talks with the other application, and there are the metrics. You can almost like the Minority Report, such a thing, and it would be absolutely doable, but absolutely pointless because usually you would like it. You would like, in one point of time to see um, monitoring data observability and not everything because you usually know what you would like to see, right? So this is
Yeah.
not like you have no clue and you're walking in the application server and look at the various parts.
But I also would see a point in this. Like, from if you're joining a new project, for
Hmm.
instance, you don't really know what you're connecting to and why. And so
Hmm.
it would be very useful. But also from the observability perspective, knowing that you're sending a lot of traffic there, it's very hot. And you
Yeah,
can look at the messages. That would be very nice.
lots of idea, no time. That's the problem, right? So
I bet there
okay.
are some tools for messaging stuff for this.
Yeah. So Morbread is already cool, and I'm already happy because I really like the Xcali draw with AX, so EX Kali draw. And it
Yep.
seems to be Plus. This is like paid software,
Yeah,
and
the
but
paid
it's on
version.
GitHub. They have 111,000 stars on
Yeah,
GitHub. Crazy.
it's now very popular. Like every other picture you see on LinkedIn about architecture is probably they use Excalibur. It's just very
Hey, we
simple.
can quit the podcast. It's all done because this seems to be nicer than Draw.io. So, and I need to create some diagrams soon. So I'm already looking forward to this one.
Yeah.
It's pretty cool. So, MIT license, lots of stars. This is on GitHub. I will put it in the show notes. Really interesting.
Yeah, so the
Mhm.
Plus version is with their backend. It allows things like two people working
Mhm.
simultaneously on the same board. I think they even have some video, maybe. I don't remember, but they have additional, like, quote unquote enterprise features. The open source version is basically the whiteboard, and that's it. It's only the
Uh-huh.
UI component.
Um, Great business model, right? Because for single developer, you can just draw. But if you would like to collaborate, there's a larger team, and it's okay to pay. I would say.
Yeah, yeah. So even just storing a list of boards,
Mhm.
because the free version is you just draw, it's stored in the browser, you refresh, it's still there. But if you want to store it like permanently, you would generate a link. But
But
people
can
would
you store
probably,
it locally? So on file
yeah,
without
as a
on the backend?
JSON or as a picture.
Okay, this is what I'm interested in. So that's
Yeah, you
to
can
have in this.
even, like,
Mhm.
the nice part. I don't know why
Mhm.
editors don't do this all the time, but you can actually select the part that you want, and you generate the picture only for that part.
Yeah, this is what Droyo does. It is you can
Okay.
select and say export selection, and this is what happens.
Okay.
Cool. So we covered Molbread. What is Meave
Mave, I call it.
or Mave?
Yeah. This one is so in a typical pharma company, you have plenty of software, and usually people don't understand how to gather information about their molecule from all this software.
Mhm.
They oftentimes work only with a limited number of software, and if someone in, like, you're a chemist and there's some other type of chemist and they work with that set of software, but you don't have access, or it's not easy, or you don't know how to use that software, you don't have the full picture. And also, when you build your software, you don't know which services to go to get the information about the molecules. So Mave is supposed to be like all the events from all the software in the company that happen to your molecules, which means they could have been synthesized or just sketched, or maybe they were analyzed, or maybe you already have a vial with pure substance. All that is captured somewhere in the software, in different systems, in different databases. So the idea of Mave is to centralize this part. So every time something happens to your molecule, you record it as an event, and then you can search it in a single place.
And how this works, it would mean that everyone who works with a molecule will have to use Mave to
Either if they're doing this manually, then yes, they can go just search and see what happens to their molecules. Sometimes this makes sense because if you have a project, you're experimenting with different hits, different modifications, you can look up that molecule and see that some other team actually synthesized it.
But how? Also, because the other thing, let's say I know molecules is Java jars. So I created a jar, right? And you would like to know when it was built or whatever.
Yep.
So I would need a plugin to report back to a central location that you know that something happened. You know what I mean?
Yeah. So the way we do it is you draw the picture, or you upload the picture that you want to search for. It finds it, and then there are links to the actual software where the information is stored in more details. And if someone worked on that molecule and they think it's a bad idea, you have the username, you have the information in their, they call it notebooks, where they store the synthetic information. You can either inspect it yourself in that software or just ask that person for more info.
So the teams are checking out virtually the molecules, do something with it, and check it back to the central location, and the event is captured. So how they report back? Let's say I would like.
Yeah, people the IT departments would have to write the ETLs. So no magic there. Yeah, every time someone is entered in one software, it has to be ETL'd back into the central system, and then you have this registry of events.
So it is more like the companies are forced, or not forced. It is good practice in chemistry to maintain such molecules in a central location, right?
This is the problem. This is the problem because there's a location where you store everything that was synthesized, and you assign some identifier there. There is a system where you put the synthetic information about how you did the synthesis. There's a system where you store the information about bioassays, whether it actually worked with a protein. So it's all in different systems. So, yeah.
This reminds me on a business model for application servers. As I started in an insurance, as a consultant back then, they wanted from day one have an application server. And I say, why you need application server? And they and the only business case was because the insurance had there were several buildings, and the mathematicians in the buildings, they created their own insurance were not coordinated. Sometimes the calculations were completely different. And what they wanted to have is one application server with the software running in central location, in order that all the critical formulas and the applications caring about the calculations run in a central location. So it seems to be a very similar problem.
So it's 2005. But by application
2000,
server...
No, 2005. This was more 2001.
And by application server, you mean...
this was WebSphere. I think it was WebSphere. So it was a Java EE application server with JMS or whatever, and the software was created for the calculations, so it's run. Back then, it was like distributed system, and this was the problem.
Yeah. I mean, every time there are two departments that can do the same stuff,
they will
do the same.
They will do. This is why, and yeah, exactly. So, I got it.
Think,
But I think what is missing maybe is like central place where such a virtual digital twin maybe of such a molecule resides, and the teams are forced to check it out, and this thing will emit an event and store it in Mave.
Yes, and I would prefer it the other way around. So if you are building your software, If you draw something there, it immediately goes to Mave and checks whether someone else has done something to
Also
that
cool.
molecule.
Yeah. But this is like my was pessimistic approach, yours optimistic approach, or pessimistic and optimistic logging. So someone will have to check it out and okay. So it means you need integrations to the other software.
Yeah.
So Molbret could be integrated.
Molbret can be integrated. Pixel can be integrated. Yes.
Yeah, super cool. And Pixel was the flagship.
Yeah, it's a big one. We've
this was what we
years.
talk about with the instruments parsing and gigabyte of files.
Yeah. With
Crystalline.
the Molbret, like you take a ScalaDraw, you take some already existing editor, you combine them. Of course, you build some database, but it's like a couple of months' work. This is not hard. Molbret is also
but nothing is hard. But in one point of time, you have to decide: would you like to spend time with how it's called ScalaDraw or on research? If you do the work, so then you are faster than scientists. So the added value is just pick the software and go.
Yeah, and also you'll have to probably at some point modify ScalaDraw for your needs as well. This is what happened.
But they could hire you, and you could do it for them, right? You could customize the okay.
Yeah, of course.
Then Crystalline. And this is an interesting one because you can grow crystals now in Java.
Oh, so this one is a very new topic. So with the chemical structures, with the synthesis, I've been working for now 10 years. I understand.
So are you more a how is it called? Chemist? Chemicant? How is it called? The guy who does chemistry? You are a chemist. Chemist.
No, I'm not a chemist.
Are you more a chemist or more a software developer?
I'm a software developer. I learned chemistry through YouTube, Khan Academy, and Coursera. And in the lab when I was shadowing people and trying to understand what they're doing.
Mm-hmm.
So chemistry is one thing, and this crystalline is a completely different part of the drug discovery.
Okay.
So let's say you have a protein and you want to understand, it's within the body, you more or less understand what it does, but you need to understand a detailed structure where you can bind to that protein to potentially break it, stop it, or vice versa, activate it.
Mm-hmm.
So, and this is most of the drugs. They attach to the protein and it folds somehow and either is activated or inhibited. So it doesn't work anymore. For that, you need the structure, and for that, you need to figure out that structure. So what people are doing is very cool stuff. Like they take that protein. They don't know yet maybe the structure. They understand the structure in terms of what chemical structure. So when protein is being built by the body, first it's built out of 20 bricks, 20 types of bricks called amino acids.
Mm-hmm.
So, and it's like, you take one amino acid, you attach second one, then third one, then fourth one. It's basically a single string of amino acids. It's going to be huge.
Mm-hmm.
And then it starts folding and forms out of this one string. It folds a 3D structure, and that looks oftentimes like a blob of stuff.
Mm-hmm.
And you as a scientist, you may know this string, which amino acid is connected to which amino acid, but you don't know how it folds in 3D.
Mm-hmm.
So what you do is you want to shine some light on it, like X-ray light. It reflects, and by those reflections, you're trying to figure out the form of that protein.
Mm-hmm.
First, before, if it's at room temperature, you cannot do this already because it's a moving thing. It jiggles. So what you want is to cool it down to very low temperatures with liquid nitrogen, oftentimes. And you also want it to form a crystal. A crystal is basically atoms that form some structure but it's not a molecule. A molecule is it's harder to explain before before doing some small chemistry intro, but basically a sugar crystal or a salt crystal, this is more like a crystal, right? And proteins, they can also form crystals. They don't necessarily are very rigid. They're more like...
Is a crystal a molecule and every molecule a crystal, or are these two different things?
These are different things.
Okay.
Molecule is about atoms connecting to each other.
Uh-huh.
And crystal is also like... But they're just arranged in some lattice, we call it.
So in molecule is more like the atom forces, and in crystal are other forces in place, right?
It's a little... I would have to do like a 10-minute intro to chemistry to explain the difference between like different types of bonds. But anyway, it's a crystal. So first, you have to spend time growing those crystals. Basically, you put a lot of protein into a liquid, and you very slowly you evaporate that liquid. And you hope that the molecules will arrange each other together with each other into some lattice. If they do, you get yourself a crystal, and if it's a nice crystal, you cool it down to very low temperatures, and you send it to some facilities. Those facilities, like these huge synchrotrons, they like a kilometer in diameter, a tube that is circular, and the electrons or some other particles go in circles, and when they do a turn, if it's like a linear thing, then there's maybe no acceleration, and it just goes straight. But if it's a circular thing, because it changes the direction, this means acceleration, and this means electromagnetic.
Similar to CERN?
Yeah. But CERN is much bigger.
Yeah.
That is a huge thing. Yeah. These are smaller. It's just kilometer in diameter.
1 kilometer is still
maybe
still
half
huge.
A kilometer.
Yeah,
it's
even
still
half
huge
a
for us.
Yeah,
huge for us. But what is CERN, like 12 kilometers?
Yeah. This is huge. But I didn't know that there's actually a smaller CERNs, also working for chemistry.
They do all sorts of experiments, but you need like very high quality X-ray, very stable, very higher energy than usually you can do in a smaller building. It emits some X-ray, and that X-ray is pointed through the crystal, and that crystal it reflects the light, and you turn that crystal slowly, and you do many, many reflections, and from those reflections, basically you have a lot of dots, and somehow, I don't know the mathematical procedure, but this is crazy. Basically, you have a circle with many dots on it, and somehow, from these many dots, they reproduce a 3D structure of that protein.
Super cool.
That's the crystallography. This is one of the approaches. The other approach is called electromagnetic.
How big is the crystal?
So it's very small usually. Like you see it with a naked eye but you usually work with a microscope. They gave me once try to fish it, because first of all you have it in a container. And then you need to fish out that crystal somehow and put it into another container to send it to that facility. So you take a microscope, you take a tiny lasso on a stick. They call it a wand, and then you try to fish it out, but it sticks to the sides that small lasso can fold. Like there's so many. It's very complicated, tedious procedure to fish it out. So it was a lot of fun. I couldn't succeed, but
and it is it has to be cold, but otherwise it would be like a glue, right? Or
so it's not cold when you fish it out. That is more room temperature.
Okay.
So it's not a glue. It's squishy, but it's holding together. It's more like a gel.
Okay.
But this jelly bean that is, it forms actual structure. Then once you fish it out, the reason you need to fish it out is you put it into a special container, and then you put a liquid nitrogen.
And the entire container is then rotated in the...
So the way they do it is you have like a puck, like on a hockey puck, with many holes. Well, 16 holes, and you take that lasso with the crystal, and you put that lasso right in there, and you ship that container together with that lasso with a wand, well, part of the wand, and then you take out that wand, and then you put it into synchrotron, and then it starts rotating. And that puck, that's what gets cooled down.
And why they ship the lasso as well?
Because you fished it somehow, and you need to put it onto some robotic arm that rotates.
Oh, the molecule is still on the lasso, or the crystal is still on the lasso?
The crystal is on the lasso, yeah.
Okay. Interesting. So it's highly
very cool,
actually.
very cool. Very new stuff. I spent like 3 weeks studying the process. But yeah. The mathematical procedure is probably the most
what
exciting.
Crystalline what are your software is doing now?
So you need to record the conditions to grow the crystals, because it's a very slow procedure. You don't do this one condition at a time.
How slow is it?
It could be a week.
Okay.
So you would take, we call it plates. A plate is basically a plastic thing with many holes, and each hole is like a vial. So small holes, you put the liquid there. It's a special kind of plate that specifically for crystallization. You put the liquid there with the protein, a couple of other liquids. You put into some, they call it hotels, where they put those plates. This is where you grow. But each of the vial can have different conditions, like different solvent, different concentrations. So you try to figure out in which conditions it works best. And it's possible that none of them works. It's possible that one of them works. That's why you do a lot of them. So you need to record those procedures, which substances you put in which concentrations, in which well. So you document this in Crystalline, and then it's possible to use it for further data mining. And also you need to store the results of actual X-ray measurements. They also go back into.
And Crystalline does it automatically? Is it working with the instrument, to capture the temperature, or is it manual?
No. Unfortunately, at the moment, it's usually either entered manually or more often uploaded as some.
So it's more like CMS right now, Crystalline, right? It's content management system a little bit.
Yeah.
And everything we talk about is implemented in Java.
Java plus JavaScript, of course. But yeah.
Yeah, front end is JavaScript.
Yep.
And backend is Java with minimal dependencies, right?
Yeah, we try to do it as well. At the moment, I wouldn't say, like, if you include Spring, and we at the moment use Spring, it's already not a minimal, I would say. But yeah, trying to do as few as possible.
And how big is the team? How much you develop of the software? So
the team is 6 people. Me and 2 other guys are backend developers. Well, we're trying to do full stack. There are a couple of people who do only backend or only front end, but we're trying to do full stack. And a couple of QAs. So 4 developers plus 2 QAs.
I do development,
but rarely.
How much of the code you developed?
Less than others. I usually would do reviews more and do the architecture and task description. And then the actual development is usually done by someone else.
Have you had the chance to try out Quarkus?
I wanted to before this call, but eventually I didn't have enough time.
You have just to launch it, you will see. So I actually did it yesterday to explain that it was a session. So I started Quarkus and explained that it could run on bare metal, Docker, and the native compilation. So I thought about you. But next time we should talk about it. What also interesting is you compared Java performance with Rust, which also is an interesting topic. So I saw this on LinkedIn, and So business-wise, what companies can do? I see you are looking for sponsors, right? So what means sponsors? So how companies can give you money? Because there's open mall events, HPLC prep, high-res mass spec, web-based NMR, cryo and workflow, HD design execution. What what is that, these sponsors, and how companies can help you?
So biotech is a very poor field. There's
Okay.
not much money there to build very good software for a long time. The business model that I'm trying to pursue is one company needs to start a software and they
Mm-hmm.
invest and they
Mm-hmm.
get the software and we give it for free and they afterwards they use it permanently for free.
Mm-hmm.
Then maybe some other company wants that software but maybe with more functionality, and because the first one ran out of money for that project. So maybe then the second company sponsors, and then
Mm-hmm.
the first company already receives the updates for free, and then the second company is sponsoring and adding features for them,
Mm-hmm.
and then maybe we have a third company, etc., etc. So we call these sponsorship because
Ah, okay.
they basically sponsor the development of software for us, but they don't own the software.
But this is a wise model
I think so.
because,
I think so.
yeah, I think so too. This is what I said, because what you are preventing are forks. The problem is if you do it differently, the company owns the software and then they fork it, and then you implement it further. You implement new features, and they can never ever integrate.
Exactly.
So your model is I like your model because you get updates for free, and as a sponsor you can request new features. It will be like the classic open source model even.
I don't know how classic it is.
No, I mean, no, what works, right? Yeah.
So far, like we had one company doing this kind of sponsorship, but I struggled to find the second company who would continue that product.
Yeah, but now you
But
get 10 after the podcast, maybe. If there's
hopefully,
some
yeah.
chemists are listening to the podcast, maybe it could work. And in one point of time you can sell support, because if this is an important project, this is also a valid business model. You're going to say, look, if you need no features now on priority or whatever, you can also sell support, and nothing prevent you then to package it and sell it as a suite of product, like
Yep, that's the point. Yeah,
yeah.
and people who didn't invest like as sponsors, they pay for a subscription. But
Yeah.
people who did invest a
Yeah.
lot as sponsors,
Mm-hmm.
I think they're eligible to just
Yeah.
use
Yeah.
software forever. Yeah.
Pretty cool. So I will have to reinvite you back, because today I was just curious about science. And next time we can talk about, for instance, performance of Rust and Java, just what you did
Mm-hmm.
briefly, and also your test strategies is also interesting, because
Oh,
you
yeah.
said my is reverse, agile, whatever, just about software more and
Yep.
less about science.
Yeah,
So I can
continuous integration, delivery.
Yeah,
all these,
exactly.
very
So I
nice
think we will
topics.
have complete opposite point of views, but it's cool. So this is what I'm looking for,
Yeah.
and just to have a sparring partner. So where people can, how people can sponsor you? What's the process to give you money? And what's your pointers on social media? The name of the company is elsci.io. This is the website, right? And I will also put it on the show notes. It's also in the show notes of the last podcast.
Yeah, usually people just would need to write an email and then we have a call, discuss what needs to be done.
Mm-hmm.
Ideally, we visit the labs as well, if possible. But if it's a very familiar field for us, like if it's a medicinal chemistry, what we were talking
Mm-hmm.
the most of the talks were called, this part of the process is called medicinal chemistry.
Mm-hmm.
We already are familiar with this, so no need to for the labs, or if it's on measurements like analytical measurements. Yeah,
Mm-hmm.
but there are some workflows like the one that I was talking about, crystallography. This was very new to me, so we had to visit the labs. But
Cool.
then signing contract. That's it.
Thank you a lot, and see you maybe in January. So
Okay, looking forward to it.
bye.
Bye.